Okay. Good afternoon. Class begins. On Wednesday, we have began to study the chapter 3, data link layer, where we first begin. We have the first time to begin to talk about some protocols. In physical layer, there's no protocols we have talked about. So on chapter 3, probably there are several protocols we will study. For example, there are these points we will talk about. First, the overview of data link layer, design issues, including principles and goals of data link layer. Then point 2 and point 2 is about error control, including detection and correction. Point 3 is about some protocols, especially with sliding window mechanisms. Data link layer is used. Data link layer protocol is used for flow control. So error detection and error correction, and flow control with sliding window. Then we will talk about some specific example of data link layer and protocols. So in this chapter, we will study the design principles of data link layer. In the data link layer, the unit of information is called frames, rather than individual bits in the physical layer. Then the data link layer uses the service of the physical layer, because the data link layer is over the physical layer and uses the service of the physical layer to send and receive bits over communication channels. So the data link layer has a number of functions that is also the goals of data link layer, including providing a well-defined service interface to the network layer, dealing with transmission errors, and regulating the flow of data so that slow receivers are not swamped by the fast senders. So the data link layer will talk about interfaces, error control, and flow control. These are three main issues. To accomplish these goals, the data link layer takes the packets it gets from the network layer and encapsulates them into frames for transmission. So, for example, this is a network layer, this is a data link layer, this is a physical layer, this is a data link layer. The data link layer, and this is a network layer. So data link layer serves the network layer and uses the service of the physical layer. The data link layer takes the packets it gets from the network layer. Takes the packets from the network layer and encapsulates in the frame and delivered to the physical layer. Then the physical layer will transmit it to another machine. Another machine then from the bottom to the top. We assumed this is the sender, then this is the receiver. Okay. Each frame contains a frame header. This is a frame header. Each frame contains a frame header and a payload field for holding the packets. The packets is taken from the network layer, then appended with a frame trailer or tail frame trailer. The frame management forms the heart of what the data link layer does. So we assume this is a sending machine, this is the receiving machines, or sending machine marked with A, this is receiving marked with B. Then this is a network layer. So data link layer takes packets from the network layer and encapsulates a frame. A frame including a header, payload field, and a trailer. Then delivered to the physical layer. Then delivered to the physical layer. And transmitted on the physical channel. Then to the another end, the physical layer, the data link layer, the network layer, etc. So in this chapter, we will talk about what is the principles, design principles of the data link layer. The data link layer service interface. That means what the interfaces and some control mechanisms includes error control and flow control. Services provided to the network layer. Service of the data link layer provided to the network layer. This is a network layer. A network layer, this is a physical data link layer. And this is a physical layer. Network layer, data link layer, and the physical layer. Then the function of the data link layer is to provide services to the network layer. What is the services? Data link layer provided the services to the network layer. That means if the network layer wants to send a packet, then the data link layer can take the packets and transmit it to the peer entity data link layer for the network layer. So that is a service. Then on another end, if the data link layer received a frame from the physical layer, then the data link layer can take the packets from its payload field and deliver the packets to the network layer on the receiving end. So that is the function of the data link layer is to provide services to the network layer. The principal service is transferring data from the network layer on the source machine to the network layer on the destination machine. Now this figure 2, illustrates the virtual communication and the actual communication view. The job of the data link layer, the function of the data link layer is to transmit the bits to the destination machine. So they can be handed over to the network layer. So on the data link layer, on the view of the data link layer, the frame is transmitted to the peer entity of the data link layer of the receiving machine. But actually, the signal, the data stream, is delivered or transmitted from up to bottom, then go through the physical channel, then from the bottom to the up, then to the application layer. So it is difference. There's differences between the virtual view and the actual view. The data link layer can be designed to offer various services. That means what's the characteristics? What kind of characteristics of the services provided by data link layer? What is the characteristics of the services from the data link layer? So data link layer can transmit a packet or frame for the network layer. But what kind of services? Reliable or unreliable? Real time or not real time? So the services includes these three kinds of services. They are unacknowledged connectionless services. Unacknowledged, that means the receiver does not reply to the sending machine. The connectionless means at the beginning of the communication, there's no need to establish a connection in advance. Then the second one is acknowledged connectionless service. Acknowledged, that means acknowledgement or reply is needed. Then connectionless means no need to establish a connection in advance before communication. The third one is acknowledged and connection-oriented. Acknowledged means this kind of service means the receiving machine will reply to the sending machine if received a frame. And connection-oriented means before communication, the two ends should establish a connection, just like a circuit switching. For example, this is A, this is B. If A want to send data to B, then A send a small frame to B and say, I want to send data to C. B reply, okay. Then A will send data to B. Will send data to B. So this is a connection-oriented. That means this stage, the connection is established. Then they begin to transmit data. So we will illustrate the details of the three kinds of services. Unacknowledged connectionless service consists of having the source machine send independent frames to the destination machine without having the destination machine acknowledge them. The example is Ethernet is a good example of a data link layer that provides these classes of service. Ethernet uses the unacknowledged connectionless service. Because Ethernet is a kind of local area network, the condition of the network is not words. So the quantity of service of the Ethernet is not bad. Have some considerable performance. Then the second one is acknowledge the connectedness service. When this service is offered, there are still no logical connections used, but each frame sent is individually acknowledged. That means if the receiver received one frame, then acknowledgement should be sent to the sending machine. Then that means each frame has its sequence number. Each frame has its sequence number. The sequence number are different from each other. So in this way, the sender knows whether a frame has arrived correctly or been lost. For example, in the wireless network, in the wireless local area network, especially Wi-Fi, it's a good example of this kind of services. And the third one is connection-oriented service. Is perhaps the most sophisticated service, which the data link layer can provide to the network layer. So most sophisticated is most complicated service, because the connection-oriented mechanisms need connection establishment. With this service, the source and destination machines establish a connection before any data are transferred. Each frame sent over the connection is numbered. That means each frame has its sequence number, and the data link layer guarantees that each frame sent is indeed received. Furthermore, it guarantees that each frame is received exactly once, and that all frames are received in the right order. So that is why the connection-oriented service is most sophisticated service. It guarantees these properties: reliable, right? Indeed received. That means the frame delivered is reliable. Indeed received. If not received, the frames should be retransmitted, transmitted again. Exactly once means if a frame arrive at the receiving machine, then receiving twice, then the only one copy of the frame will be delivered to the network layer. That means exactly once. All frames are received in the right order. That means the service, this kind of service is reliable. So reliable means indeed received, and in the right order, in order. Then the method to ensure the reliable delivery is numbering. is the numbering. It depends on the mechanisms of number. Connection-oriented service thus provides the network layer processes with the equivalent of a reliable bit stream. It is appropriate over long, unreliable links, such as satellite channels or a long-distance telephone circuit, because the satellite channel and a long-distance telephone circuit is with no quantity of performance. They are usually unreliable, probably with noisy or interference in the satellite channel or long-distance circuit. So on this kind of channels, the data link layer should be sophisticated to deal with error occurring. Then, when connection-oriented service is used, transfers go through three distinct phases. In the first phase, the connection is established by having both sides initializing variables and counters needed to keep track of what frames have been received and which one have not. This is the first phase. Connection established. By having both sides initializing variables and counters. In the second phase, one or more frames are actually transmitted. In the third and final phase, the connection is released. If the two machines finish the transmitting data, the connection will be released, freeing up the variables. The variables is the resources, the memory resources in the machine. So these resources should be freed up. Some buffers and other resources used to maintain the connection. Then we will talk about framing mechanisms. To provide service to the network layer, the data link layer must use the service provided to it by the physical layer. What the physical layer does is accept a raw bit stream and attempt to deliver it to the destination. However, the bit stream received by the data link layer is not guaranteed to be error-free. Then what the data link layer should do? It is up to the data link layer to detect and, if necessary, correct errors. So it is depends on the data link layer to detect and correct errors if necessary. The usual approach is For the data link layer to break up the bit stream into discrete frames, compute a short token called a checksum for each frame. This checksum is used for error detecting or error correcting. So this checksum is used to error control, error detecting. So compute a short token called a checksum for each frame, and include the checksum in the frame when it is transmitted. The checksum include the checksum in the frame when it is transmitted. Where is the checksum is put? Then checksum usually is put in the trailer. So the header includes some control information, right? Then the packet is encapsulated in the payload frame. Then compute a checksum for the header and the packet. Compute a checksum for the header and the payload field, and get a checksum. Checksum is put in the trailer. That is what the data link layer does. So your approach is for the data link layer to break up the bit stream into discrete frames, compute a short token to call a checksum for each frame, and include the checksum in the frame when it is transmitted. So the framing mechanisms is a key mechanism for data link layer. That means how to break up the bit stream and set the flag for the beginning and the end of the frame of a block of a bit stream. How to break up and set the flag of the beginning and the end of a frame. So a good frame method must make it easy for a receiver to find the start of new frames while using little of the channel bandwidth. We will look at 4 methods. Includes byte count, flag bytes with byte stuffing, flag bits with bit stuffing. Stuffing is a byte inserting method or bit inserting. Physical layer coding violations. These 4 mechanisms usually the third one is widely used. It's widely used in the data link layer of the communication systems. The first framing method uses a field in the header to specify the number of bytes in the frame. When the data link layer at the destination says the byte count, it knows how many bytes follow, and hence where the end of the frame is. This technique is shown in the figure 3A for 4 small example frames of size 5, 5, 8, and 8 bytes respectively. That means if it's a 5, means the length of the frame 1 is 5 bytes. This is if this is a 5 means frame 2 has 4 bytes. If this is 8, that means frame 3 has 8 bytes. Frame 4 has 8 bytes. So this is 5. So the frame 1 is 5 bytes. Then this is a 5. That means frame 2 is 5 bytes. 1, 2, 3, 4, 5. Frame 3, 8 bytes means 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes. Okay, this is A. If there is, then this byte counts has the basic function for error detecting. If this is errored, if the 5 has changed to another value, if this is error occurs in this place, then the end of the frame will error, right? So the trouble with this error is that the count can be gobbled by a transmission error. For example, if the byte count of 5 in the second frame comes as a 7 due to a single bit flip. For example, 5 is 1, 0, 1, right? If this bit flip to 1, then 0, 1, 1, 1 becomes a 7, right? So 1, 0, 1 turn to 1, 1, 1, a bit error. Then the destination will get out of the synchronization. It will then be unable to locate the correct start of the next frame. That is the disadvantage. This is a shortcoming of this byte count machine. So even if the checksum is incorrect, so the destination knows that the frame is bad, it still has no way of turning where the next frame starts. For this reason, the byte count method is rarely used by itself. It's rarely used, not widely used, because it has some important shortcomings. Then the second mechanisms of framing is flag bytes with byte stuffing. Flag bytes with byte stuffing. The second framing method gets around the problem resynchronization after an error by having each frame start and end with special bytes. Often, the same byte called a flag byte is used as both the starting and ending delimiter. Two consecutive flag bytes indicate the end of one frame and the start of the next. But there is still a problem we have to solve. It may happen that the flag byte occurs in the data. That means if we take a kind of flag as the start and end with special bytes, but there is still probable the flag bytes occurs in the data. So there's still a problem. It is still a problem. So this situation would interfere with the framing. One way to solve this problem is to have the sender's data link layer insert a special escape byte just before each accidental flag byte in the data. Thus, a framing flag byte can be distinguished from one in the data by the absence or presence of an escape byte before it. The data link layer on the receiving removes the escape bytes before giving the data to the network layer. This technique is called byte stuffing. Byte stuffing is used to deal with this problem, this kind of problem, when the flag bytes occurs in the data. Of course, the next question is, what happens if an escape byte occurs in the middle of the data? The answer is that the two stuffed with an escape byte. That will be with very low probability. But the mechanisms should be used to deal with this problem, although with very low probability. Okay, let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Okay, please keep connection. Okay, continue. Just now we talk about the data link layer includes framing mechanisms such as byte stuffing, flag bytes with byte stuffing. This is the figure 4 illustrates a frame delimited by flag bytes. A header payload field, the trailer, then the flag is 2 flags. This flag before header, this flag after trailer. So between the 2 flags, that is a frame. A frame is between the 2 adjacent flags. Then the third one is flag bits with bit stuffing. This is the third method of delimiting the bit stream. Gets around a disadvantage of byte stuffing, done at a bit level, so frames can contain an arbitrary number of bits made up of units of any size. It was developed for the once very popular HDLC protocol, means high-level data link control. That is once very popular, but it is rarely used. It is rarely used now. So HDLC became a history protocol. But the framing mechanisms is valuable for research. Each frame begins and ends with a special bit pattern. For example, 0, then 61 bits, then 0. Or in hexadecimal, 7E, 7E, 7E in hexadecimal. This pattern is a flag byte. Whenever the sender's data link layer encounters 5 consecutive ones in the data, it automatically stuffs a 0 bit into the outgoing bit stream. That is the mechanisms of flag bits with bit stuffing. When the receiver sees 5 consecutive incoming 1 bits followed by a 0 bit, it automatically stuffs the 0 bit, just as the byte stuffing is completely transparent to the network layer in the both computers. So is the bit stuffing. So on the sender's machine and the receiver's machine, the sender's machine, whenever the sender's data link layer encounters 5 consecutive ones in the data, it automatically stuffs a 0 bit into the outgoing bit stream. Then when the receiver sees 5 consecutive incoming ones, then the followed by 0 bit, it automatically destuffs, delete the 0 bit. So the receiver then gets the original bit stream. Without any bit stuffed in the bit stream. For example, this figure 5, gives an example of bit stuffing. We assumed A is the original data stream, original bit stream, 011011111. So B means the data as they appeared on the line. So on the sender's machine, scan the bit stream. If 5 consecutive ones occurs, then a 0 bit inserted here, stuffed here, right? Then 5 consecutive occurs, a 0 bit stuffed. So 3 0 bit stuffed into the original bit stream. C means the data as they are stored in the receiver's memory after destuffing. So the destuffing in the receiver machine. So the receiver then gets the original bit stream. So then C equals A, although the stuffed stream is transmitted in the data link layer. Then we will talk about error control. We will talk about error control. Just now we have talked about framing mechanisms. That is, what kind of flag to describe the beginning and the end of a frame. Now we will talk about error control. Error control includes error detecting and error correction. So we came to the next problem, how to make sure all frames are eventually delivered to the network layer at the destination and in the proper order. The usual way to ensure reliable delivery is to provide the sender with some feedback about what is happening at the other end of the line. Typically, the protocol calls for the receiver to send back special control frames bearing positive or negative acknowledgements about the incoming frames. So it depends some reply mechanisms, reply from the receiver, right? So typically, the protocol calls for the receiver to send back special control frames, special reply frames, bearing positive or negative acknowledgements about the incoming frames. Positive acknowledgements, that means if the frame received is correct without error, then positive, negative sent back to the sender. That means yes. Positive acknowledgement, that means yes, it's okay. But when the frame received is error, so with error, then the receiver will say, no, there is a wrong. Please send again. So retransmit the frames. So the receiver should reply a negative acknowledgement. Negative acknowledgement that when the frame is with error. So it should be clear that a protocol in which the sender transmits a frame and then waits for an acknowledgement, positive or negative, will hang forever. If a frame is ever lost due to, for example, malfunctioning hardware or a faulty communication channel. So the sender send a frame. The sender send a frame to the receiver, right? The sender send a frame to the receiver. So the sender will wait for a negative or positive acknowledgement from the receiver. But if the frame is lost, then the receiver will wait for the receiver forever and cannot transmit the next frame. Never begin to transmit the next frame. Then what can the sender to do? This possibility is dealt with by introducing timer, just like a clock, the timer into the data link layer. When the sender transmits a frame, it generally also starts a timer. The timer is set to expire after an interval long enough for the frame to reach the destination, be processed there, and have the acknowledgement propagate back to the sender. So that is just like this. This is sender. This is receiver. This is a receiver, and sorry. So if a frame is transmitted from A to B, then usually the acknowledgement will arrive at this time point. So the timer is set from this point. Set a timer expired at this point. So the timer is set to expire after an interval long enough for the frame to reach the destination and processed. This is processed and have the acknowledged to send back to the sender long enough for this process. So this is a timer out, T out. Another important design issue occurs in the data link layer and higher layer as well, is what to do with a sender that systematically wants to transmit frames faster than the receiver can accept them. So what should the sender do if the receiver is slow, but with a faster sender, but with a slow receiver? What to do with this condition? So we need flow control to deal with this problem. The first one, feedback flow control. The receiver sends back information to the sender, giving it permission to send more data, or at least telling the sender how the receiver is doing. The second flow control mechanism is rate-based flow control. The protocol has a built-in mechanism that limits the rate at which the senders may transmit data without using feedback from the receiver. So the first one, feedback-based flow control. For example, if we negotiate a mechanism, when I talk about a knowledge point, if you heard and understand, you can say yes. Then when I heard yes from you, I begin to talk about the next knowledge point. That is a typical feedback-based flow control of the teaching. So, but for the second one, rate-based flow control, that means I make a rule for the teaching, and 1 hour, in 1 hour, I can talk about 2 knowledge points. That is rate-based flow control. Feedback, that means 2 parties. One party depends on another party, depends the acknowledgement from another party. The receiver. So the sender depends the information from the receiver to decide whether to begin transmit the next frame. That is what the feedback means. Network designers have developed 2 basic strategies for dealing with errors. One strategy is to include enough redundant information to enable the receiver to deduce what the transmitted data must have been. This strategy uses error correcting codes. The use of error correcting codes is often referred to as FEC, means forward error correction. The other is to include only enough redundancy to allow the receiver to deduce that an error has occurred, but not which error. Deduce an error has occurred, but don't know what kind of error and which place, which bit occurs error, and have it request a retransmission not error correcting. Even error occurs, but don't know which error, which bit is error. The receiver have to request a retransmission, not error control, error correcting. This structure uses error detecting codes. So which one is better? FEC is better, but FEC needs more redundancy information and more process in the receiver machine. So FEC is powerful than error detecting, but FEC is more heavy than error detecting codes. FEC is more heavy than error detecting codes. So the error detecting codes probably is night-weighted. It's night-weighted coding. Probably error detecting is more widely used. But FEC usually used in the satellite link, or wireless links. Error correcting codes are widely used on wireless links, which are notoriously noisy or error prone when compared to optical fibers. Without error correcting codes, it would be hard to get anything through. For the different error correcting codes listed here: Hamming codes, binary convolutional codes, Reed-Solomon codes, low density parity check codes. Usually, Hamming codes is widely used. All of these codes add redundancy information to the information that is sent. A frame consists of m data bits. It consists of m bits and r redundant bits. So that means a frame with m bits, right? The m bits information. Then redundancy. R bits. So this information with m bits, then appended with r bits for redundant information. This redundant information is used for error correcting. Let the total length of a block be n. The total length of the block be n. N equals m plus r. M, this is m, this is r. So the total length of the frame is what? N, right? Is n. N is m plus r, right? We will describe this as an NM code, NM code. For example, N is 7, right? M is 4, then R is 3. So these error detecting codes, for example, these error detecting codes we called 74 codes. 74 code, NM code. An N-bit unit containing data and check bits is referred to as an N-bit code word. The code rate, or simply rate, is the fraction of the code word that carries information that is not redundant, or M over N. M over N. M over N, right? So the rate is the rate is 4 over 7, 4 sevenths. The rate is 4 sevenths. 4 sevenths. 4 divided by 7. That means on the total 7 bits code, only 4 bits is useful. Only 4 bits is useful for the user. The 7 bits is redundancy information, just for error correcting. That is utilization or efficiency rate is this one, 4 sevenths, right? So the rates or efficiency or utilization of this code used in practice vary widely. There might be a half for a noisy channel, in which case half of the received information is redundant, or close to 1 for a high quality channel with only a small number of check bits added to a large message. It depends on the quantity of the physical channel. If in the optical fiber channel, then the rate is close to 1. Close to 1 means 100%, right? 100%. 100% means the rate is close to 1 if optical fiber used. Or if satellite link or wireless links, it is noisy channel, so the rate might 1/2, 50%, or even worse, below this one. This is 4 sevenths, probably is a little higher than 1/2. So this is error correcting codes. To understand how errors can be handled, it is necessary to first look closely at what an error really is. Given any 2 code words that may be transmitted or received, say these 2 words, code words, it is possible to determine how many corresponding bits differ. In this case, how many bits differs. how many bits? For example, 1 is the same. 0 they are same. 0 1 1 they are different, right? 0 So we can use XOR calculation. XOR calculation easily get the count of the number of the different bits, right? It's very interesting. It is a very simple method. Then Hamming distance is an important concept. The number of bit positions in which two code words differ is called the Hamming distance. If two code words are Hamming distance d apart, it will require d single bit arrows to convert one into the other. The error detecting and error correcting properties of a block code depend on its Hamming distance. So what is the concept of Hamming distance? The number of bit positions in which two code words differ. For example, the number of different bits is 3. The 3. That means how these two code words are different, how they are apart from each other. So the number of bit positions in which two code words differ is called the Hamming distance. If two code words are a Hamming distance d apart, it will require d single bit arrows to convert one into the other. The error detecting and error correcting properties of a block code depends on its Hamming distance. To reliably detect d errors, you need a distance d plus 1 code, because with such a code, there's no way that d single bit arrows can change a valid code word into another valid code word. When the receiver sees an illegal code word, it can tell that a transmission error has occurred. Similarly, to correct d errors, you need a distance 2d plus 1 code, because that way the legal code words are so far apart that even with d changes, the original code word is still closer than any other code word. That is the principle of Hamming distance. So this is about the Hamming distance. As a simple example of an error correcting code, consider a code with only 4 value code words. Just this 4 code words. This code has a distance of 5, which means that it can correct double errors or detect quadruple errors. If the code word this one arrives, and we expect is not in these 4 codes, right? Is the 5th code. It's not similar with these 4 codes. So if a new code arrived, we expect only single or double bit errors. Expect only single or double bit errors. The receiver will know that the original must have been this one. So the receiver can correct the code. But with this expectation of only single or double bit errors. So that is what the Hamming distance work. Next time we will talk about CRC code, cyclic redundancy checks, and we will talk about the computation procedure in detail, especially CRC code. We will talk it next time. So much for today. Thank you. Bye.